The COMSOL multiphysics allows us to simulate a mass damper spring system under external forces. For example, as shown in the figure on the right, we can apply a force in the z direction or y direction to a cantilever beam and evaluate the resulting displacement and phase as a function of the input frequency. This type of simulation is highly useful for the design and analysis of actuators or sensors where forces are applied in specific directions. Before diving into the simulation, let's briefly discuss the numerical analysis behind it. If we denote the displacement at the tip of the cantilever as ut, the solution of difference equation is expressed as the sum of the homogeneous solution and the particular solution. The homogeneous component, ut, decays exponentially over time, and once the system reaches steady state, the response is determined by the particular solution, ut. The displacement u and the phase angle of the cantilever can be expressed as follows. This behavior can be visualized more clearly in the time domain graph shown here. In the initial state, the cantilever's motion may vary depending on its initial conditions. However, as time progresses, the system reaches a steady state, where the displacement settles into a consistent, periodic response, as you can see. It transforms this time domain behavior into the frequency domain, allowing us to evaluate how the system responds to inputs at different frequencies. In this video, we will cover the following topics. Frequency domain study to simulate the mechanical response of a structure under harmonic excitation. How to apply directional forces to a cantilever beam in order to excite the first, second, and third vibration modes. How to modify the model configuration for different setup. Post-processing techniques to visualize results by plotting multiple datasets in a single graph, including displacement and phase across frequencies. For the geometry, we have modified the original cantilever structure, which was 100 micrometers by 10 micrometers, by adding a triangular-shaped tip at the free end. In the parameters section, in addition to the original parameters such as length, width, thickness, and loss factor, we have added a new parameter, external pressure. Next, in the solid mechanics section, we need to add a boundary load. As shown here, you can specify the input force components separately in x, y, and z directions. This allows us to selectively excite different vibration modes by applying directional loads to the cantilever tip. The mesh settings remain the same as in the previous model file. In this simulation, we have defined two separate studies, one for the z-axis load and another for the y-axis load. In Study Step, you can click on Modify Model Configuration for Study Step. This feature allows you to disable physics features that are not needed for a specific simulation. By doing so, you can efficiently run separate simulations for the y-axis and z-axis loads without duplicating the entire model. Finally, in the Results section, we configure a single 1D plot group to display the solutions from both Study 1 and Study 2 on the same graph. This allows for a direct comparison of the system's response to z-axis and y-axis loading conditions. As shown in the graph on the right, the z-axis force excites the first and third resonance modes, whereas the y-axis force excites the second resonance mode. This clearly demonstrates how different loading directions can selectively activate specific vibration modes in the cantilever. Let's get started.